Assalamu alaikum. Sedimentology, Part 2, sediment, transportation and sedimentation, Bedforms, sedimentary structures, and paleocurrent analysis. Presented by Khaled Amrouni, PhD in Geology from Texas A&M University, and Khaled Amrouni is a staff member at the Department of Earth Sciences, Garyounis University, Benghazi, Barqah State, or Cyrenaica State. References for this talk: Applied Sedimentology, Sedimentary Petrology, and Essentials of Geology. This is the Department of Earth Sciences at Garyounis University, and this is the main entrance of Garyounis University. Here's the Prince Idris Senussi, the Prince of Cyrenaica State and the founder of Garyounis University. And here's the flag of Cyrenaica State behind the Prince Idris. This is the capital of Cyrenaica State, Benghazi. And this is Omar Mukhtar, the chief commander of the Senussi army. And this is the map of Cyrenaica State or Barqah State. Outlines of this lecture. The outlines: introduction, laws of physics, government, sediments, transportation and deposition, Stokes law, which is settling velocity, Reynolds equation, laminar and turbulent flow, Froude number, lower flow regime and upper flow regime, Holstrom effect or anomaly, which is for cohesive clay bottoms, bedforms and beds, sedimentary structures, sediments, texture and fabric or grains, texture and fabric, aqueous process, water, transportation process, sedimentation from traction currents, and then sedimentation from high density turbidity currents, and then from low density turbidity currents, and then Eolian process, wind, Eolian sedimentation from traction, carpet, Eolian sedimentation from suspension, and then a glacier process, ice, glacier sedimentation from traction, carpet, a glacier sedimentation from suspension, and then gravitational process, debris flow, grain flow, fluidized flow, and then some extra material like important stratigraphic surfaces, and then paleocurrent analysis. Introduction. Transportation and deposition of sediments are governed by the laws of physics. Laws of physics govern the behavior of a granule of solids in fluids, granule solids, which is sediments. Transportation and deposition means sedimentation, and sedimentation effect on fabric and structure of deposits. Sedimentation simply is the settling of solid matters in a liquid. Sedimentary process. They are the process that transport and deposit sediments. The sedimentary process include the work of 4 agents: water, wind, ice, and gravity. Since we are studying sediments transportation, we need to know the range of sediments grain sizes we're dealing with. We're dealing with a gravel, more than 2 millimeters in size, and then sand size, coarse, medium, fine, which ranges from 2 millimeters down to 0.0635 millimeters. And then finer than this is silt and clay size. Here's the sand size between 0.06 millimeters up to 2, so these 3 boxes, fine, medium, coarse, and then above 2 millimeters, gravel size, granular, pebble, and then cobble and boulders, and then below 0.06 silt size, and then clay size. And this figure explains sorting. When you have many different grain sizes together, that's poorly sorted, and when you have almost one class of the grain size, that's very well sorted. And here shows the angular and rounded. When you have no edges around the grains, that's angular. Rounded or well rounded. And when you have edges around the grain, that's angular. And here explains the grains and matrix. Grains the big size, matrix are the smaller size or finer sediments. The same thing, particle size or grain size. Here, bed forms and beds. Sedimentary structures, sediments or grains, texture and fabric. What's bedforms? Bedforms are primary depositional morphological features, individual morphological features, or topographic elements, such as ripples, dunes, plain beds, untied dunes, and pool and chutes. These bedforms produced at the interface of the interacting flowing fluid, which is air or water, and the movable loose sediments. So we have fluids interacting with movable loose sediments, and they form ripples, dunes, plain beds, untied dunes, and these we call them bedforms. Bedforms' vertical height varies from millimeters ripples to several meters dunes. Bedforms are the main building blocks of any sedimentary bed or layer. Each bedform produces specific sedimentary structures. Ripples produce cross-lamination. Dunes produce cross-bedding. Flat, plain beds produce lamination and parting lamination. Untied dunes produce low-angle cross-bedding. Pool and chute produce erosional surfaces. So flowing fluids, which is air, water, the behavior of flowing fluids control bedforms. Bedforms control sedimentary structures, textures, and fabric that control the depositional process. So the main goal is porosity. Flowing fluids, which is the velocity and viscosity of the flowing fluids, and the density and the grain size of the movable loose sediments and the channel depth are very important parameters in understanding the laws of physics that govern the behavior of granular solids in fluids. Bedforms and beds. Sedimentary structures refers to large-scale features of sedimentary rocks resulted by physical, chemical, and biological processes. Sedimentary structures refers to sedimentary features as primary and secondary sedimentary structures. Primary physical sedimentary structures include microscopic, fabric scale, and megascopic, inorganic and organic. And secondary, which is formed chemically due to diagenesis or in concretions, or deformational. And we'll study all these sedimentary structures. Textures refers to grains or grain size, grain parameters, grain morphology, grain surface texture, and grain and sediments fabric. And all of these texture, has direct relationship with the porosity, primary porosity. Fabric refers to grains, packing orientation, and contact nature, or refers to the way in which the particles of the sediments are arranged, and also related to primary porosity. Bedding. Bedding is happening due to vertical differences in lithology, grain size, or more rarely, grain shape, packing, or orientation. Beds are distinguished from one another by lithological changes. That's what we do in the field, lithology. So the syndepositional or sedimentary intrabed structures, sedimentary structures, are of 5 categories: massive, flat bedded, cross bedded, laminated, and cross laminated. So what are the laws of physics that we have to understand when we analyze sediments transportation and deposition? The first law is Stokes' law, talking about saline velocity in motionless fluids. Reynolds equation, R equal 2000. Is it above or below? Talking about dynamic situation in a fluid flume or tube that shows laminar and turbulent flow behaviors. And then Froude number in open channels, which shows that there are 2 flow regimes: slower flow regime where F Froude number less than 1, and upper flow regime when Froude number is above 1. And each flow regime has different or produce different bed forms. Holostrom graph or Holostrom effect or anomaly. This is again in a dynamic situation. And Holostrom is discussing the critical velocity required to erode or the critical flow velocity needed to start a particle into motion. And this anomaly is related to the mudstones, erosion of mudstone. So let's go with the Stokes law. Stokes law say W settling velocity equals the particle density, the difference in density between the particle or the grain and the fluid multiplied by gravity over the viscosity of the fluid, 18 of those, times diameter square of the grain. And the settling velocity, and this law says a large particle will settle faster than a small one, just because it has a larger diameter. And it says the denser one will settle first. If you have two grains of the same diameter but different density, one heavier than the other, the denser one will settle first. We are assuming all these particles are so spherical. Reynolds number, it says R equal UdP over mu, and by the way, this is just a ratio. It's a dimensionless Reynolds number. U is the velocity of the particle, D diameter of the particle, P density of the particle over viscosity of the fluid. So Reynolds number is related to the viscosity. And Reynolds number shows us there are two ways, turbulent and laminar flow. When we increase the velocity, the Reynolds number will pass 2000 and give us turbulent flow. When we decrease the viscosity, the Reynolds number getting higher and will give us turbulent flow. So laminar flow, when Reynolds number less than 2000, 2K, 2000, the flow lines parallel in the transport direction. Low flow velocity will give us laminar flow, high viscosity will give us laminar flow, and smooth bed surface will give us laminar flow. Turbulent flow, actually when Reynolds number more than 2000, the flow lines intersect and not parallel in the transportation direction, the fluid flow lines. And if you have high velocity, you get turbulent flow. If you have low viscosity, that gives you higher Reynolds, turbulent flow, and rough bed surface will give you turbulent flow. So if you compare two liquids like air, two fluids, air and water, air always having low viscosity. That's why Reynolds number is so high in the air media and always giving us turbulent flow, while water has higher viscosity than air, and when the water flowing slower will give us laminar flow. When air moving faster, high speed, will give us turbulent flow. So if we looked at the tube at this figure, fluids will start moving as laminar, and then when speed increases, we'll start moving as turbulent. The flow will be turbulent, so laminar at first and then turbulent. But within the turbulent zone, under the boundary layer, they find out there are two zones within the boundary layer. There's turbulent zone down here until this blue, and then there's buffer zone where the speed decreases drastically under the buffer zone, and there's viscous sublayer. So viscous sublayer, buffer zone, and then turbulent sublayer. And each sublayer has different or will produce different bed forms. So the viscous sublayer will create laminar flow and form ripples. Turbulent sublayer here will have turbulent flow and create dunes, antidunes, and the combination of turbulent flow and viscous flow will give us parting lineation, ridges, and erosional grooves. So each type of flow will with different bit forms. Froude numbers in open channels. Talks about the speed of F equal U over root square GL. U is the velocity of the particle, L the force inertia, or force of inertia, or the distance that the particle traveled, or the grain traveled along the channel. G is the acceleration due to gravity. So, Froude number on open channels will distinguish between two flow regimes. The lower flow regime where F less than 1, by the way, F is ratio, is dimensionless, by the way. Low flow regime will produce bit forms such as ripples and dunes. Upper flow regime will produce bit forms such as plain beds and antidunes. So if you're in open channels, U will be the current velocity, and D will be depth of the channel. So here, if we look at these three examples here at the faucet sink, we'll have high-speed water, and then a boundary, and then low-speed water with waves. The high-speed water here, that's what we call supercritical, where F above 1, high flow regime. And then where you have waves here, this is subcritical, where F less than 1. In between, there's hydraulic jump or standing waves. It's the same here. You see in this pond, there's high-speed water, so waves cannot form. This is the supercritical, which is high flow regime, F more than 1, and here hydraulic jump, F equal 1, and then this is subcritical, which is F less than 1. This is lower flow regime, this is upper flow regime. Lower flow regime, upper flow regime. Same here in the flume, we'll have high speed water of the critical or supercritical zone, F more than 1, facing stagnant water or low regime water, and creating hydraulic jump. Hydraulic jump forms when high-speed supercritical water moves down to low-speed subcritical water. And the hydraulic jump, at the hydraulic jump, F F equal 1 exactly. So lower flow regime produce ripples, dunes, which is subcritical. Upper flow regime, if more than 1, produce plain beds, antidunes, and pool and shoots, which is supercritical. So, okay, so Froude number focuses on how fluids transport sediments in open channels, how gravity influences the way in which flowing fluids transmit surface waves. Okay, to find the F critical depth, U, which is the speed, rate of flow, and D, channel depth. In U of the stream, U is stream flow velocity, and G times D, the root square of G times D is wave propagation velocity. We call it wave celerity. So if we go back to this example, here the speed of water higher than the speed of wave, but here the speed of wave higher than the speed of the fluid, the water. The same thing here, speed of fluid more than speed of wave, here speed of wave more than speed of fluid. So the subcritical, whenever you want to know if the fluid is subcritical stage, so you have just drop a stone there. If you see waves forming there, and that means the flow is lower flow regime, subcritical. So if F less than 1, this lower flow regime, subcritical, tranquil flow, and always we see waves forming above these surfaces, the tranquil flowing fluids. Slow flow due to slow velocity and greater depth. Critical depth less than actual depth, or actual depth is more than the critical depth. Wave speed more than the stream flow velocity, because the stream is very slow. So upstream wave propagation. If you dropped stone there, waves will propagate upstream and downstream. If more than one, that's the upper flow regime. That's the supercritical system. That means the flow, shooting flow or agitated flow, will have fast flow due to what? Fast velocity or shallow water depth. Here, the critical depth is more than the actual depth. Wave speed less than the stream flow velocity. So stream faster than the wave, so no waves will form on the water surface. Here's the untied dunes. Same, well, the current going from left to right. And you see here the waves standing. This is the critical zone or hydraulic jump. And the waves, instead of going this way, they're coming reverse, going upstream, while the current is moving all the way to the right, not to the left. And at this stage, the untied dunes, they form. Okay, bed forms. So we have current velocity increase this way, and we have flow regimes, lower flow regime, upper flow regime. At the lower flow regime and at lower speed, we have ripples, and then as the speed increases, we have dunes form. And then after that, this is under the low flow regime, where Froude number less than 1, and then we'll start going to the upper flow regime, get plain beds, and then untied dunes. Untied dunes migrate downstream, the depth down, migrate upstream, while dunes, ripples and dunes, they migrate downstream. Okay. So here the relationship between stream power, grain size, and bed forms. As the grain size increases, bed forms change laterally, and stream power increases, the bed forms change upward. Start from ripples to dune, that's the lower flow regime, and then plain bed and untied dune. And as you go to the grain size 0.65, the ripples will disappear. So here there are bed form stability fields. Here we have field of ripples, field of dunes, field of upper plane, and field of untied dunes based on the speed and the grain size. And this is again the same figure, but here the tubes that they did the experiments were used to do the experiment. We were 0.25 to 0.4 meter depth. So how I look at them and the stability fields. If we look at this, we find ripples, they form from, like here, grain size goes up, clay, fine sand until coarse sand, gravel. So ripples, they form from clay silt size, very fine, to up to almost 0.65, which is coarse sand. But above that, no ripples. So very coarse sand, no ripples. Okay, lower plain beds start from coarse and up, but fine sediments have no lower plain beds. Dunes, they form from fine or 0.1 up to unlimited, but less than 0.1, no, less than fine sand, basically, no dunes. Silt or very fine sand, no dunes. Okay, here the upper plain bed goes from silt clay, very fine, until 1 millimeter in some experiments, depends on the depth of the flume, more than 1 millimeter grain size. But let's say it goes up to 1 millimeter. And here we have upper plain bed and lower plain bed. How to distinguish between them? The upper plain bed always have parting lineations, but they have the overlap, which is the coarse sand size. Okay, the untied dune forms from very fine grains to very coarse grains, no limit, and forms at very high speeds, and rarely preserve it because the untied dunes destroyed when the before this system deaccelerate. So we have now stability fields, and we know now these bed forms controlled by grain size plus stream powers. Holostrom graph. This Holostrom graph, they were generally thinking that critical fluid flow increased with the grain size. That means as the grain size increases, the speed needed to erode that grain will be increases. So this is settling velocity under anything under this settling velocity, depositional, and this is erosional velocity. Here grain size 0.1 like sand size until almost 2 here, very coarse sand size, and then gravel. As the grain size increases, the speed needed to erode that coarser grain will be increased. But when you come here to finer grains, we were expecting to have, or that you need just less speed to erode them. We find out the opposite. You need higher speed to erode finer silt and clay size. Like for example, you need 9 centimeters per second speed to erode silt and clay size, which is exactly the same speed that you need to erode almost grain size of 4 millimeters, which is gravel size. Why that happened? Because of the resistance to friction, the cohesion force. We call it cohesion force. So clay layers or mud layers, they have very strong bonds, made them able to resist the erosion. And this noted by Holostrom and called Holostromograph or Holostrom anomaly, and that's why we find the clay layers inside tidal deposits, coarse sand tidal deposits, preserved there, the clay layers. And here, this is another presentation for the same thing. So we have this line, depositional line, anything under is deposition. And here we have erosional line. Any loose sediments will be eroded from clay size all the way to coarser and sand and gravel. But this is for rocks. Consolidated clay will need high speed to be eroded, and then sand size, and then gravel size. So when it's eroded, even the speed if it dropped down, still transported until it drops really like substantially to be below this curve of deposition. So now we finished all the laws that governing the sediments transportation and deposition or behavior. Now we will study the sedimentary structures that produced by the bedforms. So the bedforms, as we said, ripples, dunes, untied dunes, and plain beds. So we have 4 types of sedimentary structures: erosional sedimentary structures, depositional sedimentary structures, post-depositional or deformational sedimentary structures, and biogenic sedimentary structures or ignifacious. So let's do the first one, the erosional sedimentary structures. Here, there's a very good classification for the inorganic mesoscopic primary sedimentary structures. So here, the pre-depositional interbedded, which is the erosional sedimentary structure, they call them pre-depositional interbedded, like channels, scour and fill, flute marks, groove marks, and tool marks. Those predominantly erosional. Sen depositional sedimentary structures, which is depositional, massive, flat bedded, include part inclination, graded bedding, cross bedding, lamination, and cross lamination. And then the post-depositional sedimentary structure, basically the deformation, deformed interbedded and intrabedded. Okay, slump slide, those with predominantly like horizontal component, convolute lamination, convolute bedding, recumbent foreset load structures, those with vertical components. And then miscellaneous rain prints and shrinkage cracks, which is muddy cracks and cinereous cracks, those primary sedimentary structures. We can add them with these here. So let's go with the erosional sedimentary structures. Soil structures, fluid marks, groove casts, gutter casts, which is storm deposits, scours, and channels. So gutter casts are just erosional features during storm. The periods, the storm will start, the currents will start just erode through the soft shale layers, and then when storm wanes down, the sand will start filling up these these channels or these erosional gutters with sand, and mostly this sand is showing a hummocky cross bedding, and you'll find it mud, sand, mud, and you see this gutter shape just cut through the shale and then filled with sand. Okay, and this is what we call a tempestite: shale, sand, shale, or mud, sand, mud. This is tempestite sequence. Okay, and here's a storm deposit. This is a gutter in the Miocene of Cyrenaica, which is a storm deposit too, and filled with cross-bedded grainstones. Soil marks, flute casts, and tool marks form at the base of turbidite sand beds. So this is the base of turbidite sand, and shows this is the flute marks, and this is the groove marks. The groove's just the fill of any holes, straight lines, sand fill any holes and straight lines that was at the shale layer below or mud layer below. And flutes are the same thing, are fill, but when they hit the bottom of the shale, the sand hits the bottom of the shale, starts splashing and form this flute shape, like V shape. And always this V shape telling us when tapers down, this is up dip, and when opens up, this is down dip or current direction. And tool marks, just any fossils or grains touching the bottom of the shale during the deposition will be preserved, and mostly the grains or fossils will be preserved at the end of this feature. So here we need to differentiate between cast and mold. Cast is the fill, so this is cast, the fill. Mold is the impression, okay? Mold is the impression, the empty impression. Cast is the fill. Here's explaining the flute marks, this V shape. So the current direction is this way. So this is the sketch for the flute marks, and they're on the left side, the right side, the cross section, showing you how the current's moving, and then there are holes here. The sand just hits here and splash, and gives you these V shapes. And these flute marks or V shapes, when it opens up, shows you where the current is going. And Cretaceous channel fill, here you see the smiley face here. This is a channel filled with Cretaceous turbidite limestones, and this is my student Sabra during the field trip there. We have another example from the Cyrenaica and Miocene, Barqah state. It's a channel fill, and this smiley face is a channel that's filled with grainstone, backstone sediments. And here Oligocene channel fill, and the channel fill shows larger scale cross bedding. We call it ipsum, larger scale cross bedding or lateral accretions. And this is also from Cyrenaica state or Barqah state. At the road cut, rip up lithoclastis. Rip up lithoclastis when the sediments eroded and then transported downstream and then deposited at the bottom of other beds. Gives you shows you these rip-up classes. And here we have another example of rip-up class. These circular shapes are the places where rip-up classes used to be preserved, and rip-up classes now they're weathered. So these just like traces of the rip-up classes in a sandstone of in Denver Basin. And here we have other rip-up class or lithoclast. This gypsum crystals eroded and then redeposited in white gypsum in the Cyrenaica Miocene. And here another example of the same thing, like crystals of yellow gypsum inside, redeposited lithoclast inside the white gypsum in the Barqian Miocene, in the Barqah state. Now finish the erosional sedimentary structure and go through the depositional sedimentary structure. So all bedforms, plain beds, ripples, dunes, and antidunes, these bedforms produce these depositional sedimentary structures that are generated by waves, winds, and currents. Waves in shorelines, winds in deserts, and currents in tidal and fluvial environments to produce lamination, cross-lamination, and cross-bedding, and the associated graded bedding. Their transportation mechanisms, we'll study them later: traction, bed load, high-density current, and low-density suspension current. We'll study these transportation mechanisms later. So, ripples and dunes. Any ripple has wavelength that goes from, let's here crest, and this trough crest goes from crest to crest, this is wavelength, or from trough to trough. And the height from the bottom to the top of the crest. So they have height and wavelength. If you divide wavelength over height, you get ripple index. And the ripple has a Stoss side and lee side. And most of the time, and always, ripples and dunes, they have the same shape almost. This Stoss side is the erosional, and the lee side is the depositional. So when sediments transported above here and move it from the Stoss side to the lee side, will just drop down. So this is a grain flow, this bed load sediments, grain flow, and drop down when you have grain flow. So the core, you have different grain sizes. That means fine and coarse, and based on the angle of repose, the finer ones will deposit first when you have grain flow, and then the coarser will drop after because they have higher angle of repose. And this will give you a new laminae with coarsening upward cycle. So this coarsening upward feature happens when you have avalanching or grain flow. But on the other side, if these sediments lifted up, suspended, what will happen here? The opposite will happen. The heavier ones will deposit first, heavier grains, coarser grains, okay, will deposit first, and then finer grains will deposit after that, and you will end up with fining upward cycle, another laminae, and this laminae shows the opposite, fining upward cycle. In this case, suspension, we call it grain fall. Grain fall. So we have grain flow, avalanching, producing coarsening upward layer, laminae, and grain fall, which is when the grains are suspended in the air and then falling, will produce the opposite, fining upward. And this applies for both ripples and dunes. Let's go. So here, if we look at the cross stratification, the basal contact, and the internal texture, we'll have here force set, and this one have force set and bottom set. So tangential, force set, and then bottom set. Okay, but this one has just force set and has angular relationship with the bottom, the base, but this one has tangential because it has foreset and bottom set. But this, so if we look at the internal structure here, we have graded bedding. The thick bed here shows fine to coarse. This is coarsening. That means that's grain flow, avalanching. The other one shows fining upward. That means grain fall, which is suspension. How is these grain fall layers or lamines finer and thinner, finer grains and thinner? Is the grain flow laminae, which shows the inverse graded bedding or reverse grading, coarsely grained and thicker. Also, we note these relations here. We said this is angular between the Stas side and lee side. Here we have tangential relationship between lee side and Stas side of the previous. And here we have sigmoidal between the lee side and Stas side. So why we have these three different contact relationship between or within the cross laminae of the ripples? The first one shows that all these grains, all these foresets formed due to avalanching or grain flow, and these lee sides are partially preserved. So it shows what formed these angular relationships. The second one, the tangential, it has foreset and bottom set. This is just foreset preserved. The lee set, foreset and bottom set of the lee side due to the combination of grain flow and grain fall. And part of this foreset preserved partially. Okay, here still have combination of grain fall and grain flow, and the whole foreset completely preserved, or the whole laminae completely preserved. It has bottom set, foreset, and top set. And as you go down this way, rate of sedimentation increases and the rate of migration or transportation is less, decreases. So graded bedding, we have normal, fining upward, reverse or inverse, coarsening upward, when you have massive, and we have multiple. So the massive, when you have no graded bedding due to high rate of sedimentation, we call it dumping, or due to destruction of the original internal structure by bioturbation, dewatering, and recrystallization and replacement process. And sometimes you have multiple, which is combination of normal, or many stages of normal, many stages of reverse, or combination of both. So let's look at the normal and reverse. Normal, we have two types of normal. This is normal, coarse down and fine top. Here, coarse down and fine top. But this one, if you look here, all of them almost coarse, and here fine. So it's like split, coarse to fine. But at this one, we have coarse, mix it with fine, but as you go up, just fine left, no coarse more, no more coarse. Okay, this is what we call it content grade bedding, and this is what we call it coarse tail graded bedding. They're both normal. Here, the opposite reverse. You have fine at the bottom. As you go up, you have coarse. So this is coarsening upward, reverse. This form, the fining upward, they form from the falling grains, which is suspension grains, when the currents accelerates. Here, the loaded sediments, the current loaded with sediments. And here forming from the grain flow when the current accelerating. Okay? So go next one. This is example of fining upward. You have coarse grains here. As you go up, become finer. So this is fining upward. The next example, coarsening upward. One cycle, second cycle, So multiple cycles of coarsening upward. Here in the field, if you look at this here, this boundary and this boundary here. So from here to here's fining upward. And there's another cycle fining upward here too. And was another cycle from below fining upward. So you have multiple cycles fining upward. This is the fluvial fining upward buried bedding in Wadi Zaza, Cyrenaica, or Barqah state. Now we're seeing the styles of ripple cross stratification. We have the subcritically climbing ripple cross stratification and supercritically climbing cross stratification. Here they are measuring two angles, angle of a climb and angle of Stas slope. So if we take it here, this line straight, and this is the lee side, and this is the Stas side. And we just have horizontal line here, parallel, okay, to the horizon. This big angle is beta, the climbing angle. And this angle here between the horizon and the lee side, the Stas side, sorry, is alpha. So here beta is way bigger than alpha. You can do the same thing here. Okay. Try to extend it. And then surface with the horizon, parallel. Here find out alpha, way bigger than beta. Beta very small. Second example here. And here you see tangential bedding. Okay. And here we have sigmoidal bedding, and these is what we call them climbing ripples. In climbing ripples, always beta climbing angle more than the alpha, which is the angle of Stas side. Yeah, and here we have tangential, and this is, should be, it shows tangential but should be angular. Angular and tangential, the alpha bigger than beta. So the angle of Stas slope bigger than the angle of climbing. Rate of sedimentation as you go down here, faster. Okay, rate of sedimentation faster. As we said, these form from falling. Here just for the sets of the ripples, they form from grain flow. Here, grain flow and grain fall, both. Same thing here, grain flow and grain fall suspension. Grain flow bed load and grain fall suspension, and the whole for sediment and lee side and Stas side preserve it here. Here's just the lee side, preserve it, lee side, preserve it. Rate of sedimentation increases, but the rate of movement of these ripples decrease as you go down. Ripples. Now this is a bed with the ripples at the top. See those wavy surface? Ripples. 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 Form. Ripples, bed form, and they form cross lamination. Here's another ripple limestone in the Cyrenaica Miocene or Barqah state. And here we have ripple gypsum in the Cyrenaica Miocene Barqah state. And this ripple gypsum produced cross-laminated beds. Okay, as you can see here, and these fractures just the mud cracked zones. Okay. Also, we have lamination, but this is not the production of ripples. It's a plain bedding. Okay, or due to chemical changes. So the climbing ripples, here example of climbing ripples, you see this Stas side, lee side, Stas side, lee side, Stas side, lee side. This is the climbing ripple, shows sigmoidal. High rate rate of sedimentation coming from falling and falling and flowing grains. Sigmoidal. Here we have the same thing here. Sigmoidals, beside side, and we have tangential, what ends here at this erosional surface. Another tangential one. So tangential and sigmoidal. This is cross-lamination again. Ripples produce cross-lamination. Here we have, this is in Cyrenaica, Cretaceous Cyrenaica. We have angular. Okay, and we have here sigmoidal. And we have here another sigmoidal. Angular, just foreset. Sigmoidal, foreset and bottom set. Foreset and bottom set. Okay? Cross-lamination. So beds and laminae thickness terminology. So for beds, if it's less than 10 millimeters, very thin bed, between 10 and 100 millimeters, thin bed, 100 to 300 millimeters, medium bed, 300 to 1,000 millimeters, thick bed, more than 1,000, very thick. For the same thing for laminae here, less than 1 millimeter, very thin laminae, 1 to 3 millimeter thin laminae, between 3 and 10 millimeters, medium, between 10 and 30 millimeters, thick laminae, above 30 millimeters, very thick laminae. Now, bed forms. Symmetrical bed forms, if we look at the bed forms, either dunes or ripples, we'll see either they have straight crests, okay, these straight crests, or sinuous crests, or catenary crests, or linguoidal crests, or lunate, like scoop shape, okay? These changes happening at the surface of these bed forms due to the change or increase of the flow. When the speed of the flow increases, the forms will change from straight crest to sinuous to catenary to linguoid to lunate. So the only ones we call two-dimensional straight crest, but the sinuous, catenary, linguoid, and lunate, we call them three-dimensional bed forms or three-dimensional surfaces. Okay, plain view of the ripples. So here we have the same thing, but they added the wave ripples, the waveform ripples. They have this bifurcation. Okay. So if you look at this picture from Cyrenaica State exactly from the shoreline of Batlamos City in Cyrenaica State, Barqah State, you will see this bifurcation here, very obvious in the wave ripples. And this photo by Hamad, a very creative guy, Hamad Bakar from Cyrenaica, from Batlamos City, Cyrenaica. And the waveformed ripples, they have three internal structures. They have bundle structure, this shape here, and they have chevron, where these chevron sign, okay, and they have unidirectional cross-lamination. This example, this is from the Miocene of Cyrenaica, Wadi Gatara Formation, Barqah State. We have a chevron example of the wave cross-lamination. So let me show you here. Okay. This is the wave, the chevron. Cross-lamination. And the bottom surface here is just erosion. And by the way, there is trough cross bedding here if you look at it. Okay. So this is the ripple cross, or the chevron cross lamination. and this is wave ripples. Now we have the ripple index, which is the wavelength or spacing above over the wave height. We have the ripple index for wind ripples, wave ripples, and current ripples. So mostly we find out the length or the spacing of the wave ripples between 0.9 to 200 centimeters, which is the largest, and the height between 0.3 to 25 centimeters, 1/4 of a meter, which is always the, the largest. So you can put L over H to get the ripple index for each one of them. Now, dunes and untied dune formation. Now we need to focus on the in phase and out of phase. What's the meaning of out of phase if Froude number less than 1 and in phase Froude number more than 1? Okay, this should be 1. Okay, so dunes here, if we look at the dunes, we have crest, trough, crest, trough, crest. And each crest across of it, the wave has a trough. And each trough at the bottom, the sediment surface, has a crest. So crest of the wave, trough of the sediment. Trough of the wave, crest of the sediment. This is out of phase. That's when Froude number less than 1. That happens when you have dunes and ripples. And that's why these side, the Tasa size is erosional, and the deposition always common here because of this stress, and that will decrease the viscous sublayer and create turbulent current and the deposition, and all the sediments dipping down the stream. Okay, but when you have untied dunes with Froude number more than 1, you'll find the sediment surface crest facing, or across of it there's a crest of the wave, and the trough of the wave across of it there's trough at the sediment surface. So crest with the crest, trough with the trough, they are both in phase, the wave and the sediment surface, and that's why the trough becomes higher energy zones and erosion, zones of erosion, instead of being deposition, the lee side, and sediments just deposited here. And that's why it shows up as if the ripples or the untied dunes, they are migrating downstream, because this is the erosion of the depositional place. Sediment dipping upstream. Okay? So now we understand what's the meaning of in phase and out of phase. So if we look at the shoreline in Cyrenaica, City, find these dunes, sand dunes, this guy walking along these dunes. Okay. This is a picture again by the creative guy, Barqah. Those sand dunes in Cyrenaica State, Barqah State. Again, we have sand dunes, big one here. And above these sand dunes, we have ripples superimposed on these dunes. Ripples. So what's the difference between dunes and ripples? Dunes, larger scale, ripples, small scale. Dunes coming from turbulent flow, ripples coming from laminar flow. Dunes scale up with the flow depth. As the flow depth increases, dunes getting bigger. But ripples, they scale up with the grain size. As the grain size increases, giving you higher or bigger dunes. The dune's height more than 5 centimeters, ripples height less than 5 centimeters. Dunes with length or wavelength more than 0.6 meters, ripples wavelength less than 0.6 meters. Okay, so one turbulent flow, one laminar flow, the other one larger scale, the other one smaller scale. The dunes increase in size with depth, the ripples increase size with grain size. Here's another type of dune, but in the desert, not along the shoreline. Here we have a dune, huge one, another dune, another dune, another dune. So usually it's actually a big dune with superimposed dunes on it. But this dune has ripples superimposed on it. So this is wind, these wind ripples, okay? Above wind dunes in the deserts. Now, plain bed forms. Plain bed form produce lamination. As we see it here, lamini, lamini, lamini. That's due to wave bed form. This is from the Miocene of Cyrenaica state, Barqah state. Laminated white gypsum. Here we have this white gypsum is laminated. There's deformation. Okay, this white gypsum is laminated, but later deformed. Post deposition deformation. Okay, here we have another type of cross-bedding, herringbone cross-bedding, which is very tidal. It's formed in the tidal environment. Yeah, looks like the fish skeleton. It's what we call it herringbone cross-bedding. You can follow it everywhere. This is due to the ebb and flood of the tide. Okay, now we have another herringbone cross-bedding. 1, 2, and then 3. 1, 2, 3. 1, 2, 3. Those all herringbone cross-beddings. They're from Cyrenaica state too. And this is another bigger herringbone cross-bedding. All of these herringbone cross-beddings. Okay. Another that was again from Cyrenaica, Miocene of Cyrenaica, and here is another herringbone cross-bedding, tidal flats from the western part of Triple-Tania, basically. Okay, and here we have herringbone cross-bedding, very large scale from Cyrenaica state, Barqah state. And here we have another, and this is tidal, by the way, and this is another feature we call a tree-activation surface. Do you see the surface here? Oh, sorry, it goes this way. So along this surface, you see these onlaps along this surface, and this erosional surface onlaps. In here, you find laminations again along this surface, and this surface represents erosional or erosion, period of erosion, and this happens in the tidal environment. And this is again this example from the Miocene of Barqah state, Cyrenaica. Mud couplets. Here we have mud, sand, mud, and this is very tidal, and this is what we call it the mud couplets. And mud preserved here due to the holostrom anomaly, and because mud, they have this very frictional resistance to the frictional erosion. Now there is microbial or primary biogenic, and they're primary biogenic sedimentary structure. They form as you see in the tidal environment, this shark-based Australia. These stromatolites, microbial deposits, blue-green algae. And these either planar, laminites, laterally linked, or columnar. Both of them columns. And sometimes you have oncoid, irregular circles of microbial blue-green And these bloom green algae, they are divided into dendrolites, thrombolites, stromatolites, leolites. Leolites has no internal structure, but it's made 100% of blue-green algae. Stromatolites has very distinctive layered laminated uh, structure, sometimes laterally linked or columnar, but has a structure. The thrombolite is, as as the name implies, it's just thromps and shows like irregular equidimensional clots, and they can form up to branches. The dendrite, uh, they call it shrub-like form. Okay, so these four different structures, these the domes, domal structures of these forms. So these the four, and sometimes you can find combination between like stromatolites and thrombolite. We call thrombolytic stromatolites, for example. Okay, those primary structures of microbial. Here the field trips, my field trip in Central Texas, Mason. So this whole thing is microbial structure. Shows another microbial structure. So these, and here laminated, 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 goes bed, laminated. All of these just stromatolites, microbial structures. Okay, microbial buildups. And this is another microbial stromatolite, so called the brain rock. Tidal, by the way. Another laminated, laterally linked stromatolites. And here the thrombolites, the clots, and here the coin for scale. Microbial, primary, tidal. And here stromatolites, from laminated stromatolites from Cyrenaica state, Barqah state, Miocene of Cyrenaica, tidal, goes all the way. This is at the area it's called Garyounis at the Sulug Labiar road cut. And you might find stromatolites like plain, small scale here, microbial growth, tidal. Okay. And you might have another form is called pisolite, circular. This is organic structure formed when the grains just rolled around the stromatolites, formed these circular, which is more than 2 millimeters, like gravel size, more than the sand size, but circular shape, pisolite, call them pisolite. And here, this is between pisolite and oncolite, and this is the oncolite for sure, like ball shape, irregular, microbial, still microbial. Still tidal. Here we have fenestral structure. Fenestral, which is microbial, tidal. The fenestral, these openings, fenestral, fenêtre, it's a French word, means window, so these windows. And these windows, they form due to gas entrapment, organic matter decay, and borrowing. If it's gas entrapment, you should see these as circular shapes. When they're circular, equidimensional, that means gas entrapment. But if these windows or fenêtres elongated like this is decay, organic matter decay and desiccation. And if you see them vertical, that means porous. Okay, those are the three interpretations that they have. So this is elongated. Okay, burrow. This is elongated. So this is organic matter decay and desiccation. Now we have another sedimentary structure. Rippled sand and mudstone. They form wavy ripples here when you have 50-50% sand, cross-laminated sand and silt 50-50. But as the mud increases, you'll have lenses of cross or rippled sand floating in the mud. This is lenticular. This is wavy. If the sand increases, you have sand with streaks of mud. That's what we call it, flazer. So we have wavy, flazer, lenticular. These are tidal or deltaic features. and they can happen in any place where you have fluctuation in sediment supply and flow strength. And there's example here. We have wavy in the middle, 50-50%, sand ripple sand and mud. As the mud increases, the sand decrease and the mud increase, you'll have just lenses of sand, lenticular. As the sand increase this way, you'll have just mud streaks in the sand and called flazer. So these are the three types: wavy, lenticular, and flazer. So the wavy is a middle ground between lenticular sand lenses and wavy, the completely almost sand. This is flazer, mostly sand with mud flakes. Here we have wavy, like 50-50%, sand, mud, and here lenses of sand, lenticular. Okay, sand floating in mud. Good. Now, planar and trough crossbedding. As we said, planar crossbedding form when you have two-dimensional bedforms with linear crest, and trough crossbedding when you have lunate or scoop shape bedforms, either which is dunes with scoop shape or lunate shape will give you three-dimensional trough crossbedding. Dunes with straight crest will give you planar crossbedding. Trough crossbedding form at higher velocity than the planar crossbedding. 1. 2. Trough crossbedding form at higher speed, flow speed, than the planar crossbedding. So higher speed, deeper. Now going to explain the sets and cosets. If you have more than one bed, like here, and each one of them has crossbedding, planar crossbedding or trough. So 1, 2, 3. So each bed is set. All of these three together, 3 beds, we call them coset. And they have tabular planar crossbedding. Call them tabular planar crossbedding coset. The same thing for the trough. If you have more than one bed, one bed, one, and the second, and each one of them has one set, 2 sets of crossbedding, we call them trough crossbedding coset. If you have one bed as planar crossbedding, we call it one set. If you combine all of these together, this is composite set, okay? Composite set. So we know now what's set, what's coset, what composite set. Good. So now we have planar crossbedding, and planar crossbedding has tabular, wedge, and tangential. This one is tabular when the angle is its angular relationship. No, just we have 4 sets. So this is one set of planar, and there's another set here of planar tabular crossbedding. So these together will form coset. Okay? Set together will form coset of tabular planar crossbedding. Now we have another type of crossbedding, but this is tangential, like 4 set and then bottom set. 4 set, bottom set. So this is one set, second set, third set, fourth set. Okay, so 1, 2. All of these together we call them cosets. Cosets. Okay, tangential crossbedding. In the third type of the planar crossbedding, we have wedge. So this is one wedge here. Sorry, okay, one wedge. And this is another wedge here. Okay, and here's another wedge. Okay, and these just wedges. And this is another wedge. So 1, 2, each one of them is a set, 4, 5, and all together we form 7 like cossets. Okay, those wedge planar cross bedding. And here we have planar and trough cross bedding in the Miocene of Cyrenaica Barqah state. So here, this is a planar, and this one here, immediately trough. Same bed, planar, and above it just trough. Okay, so this is composite set. This is one set. Okay, and this is different set. Together composite set. And here we have trough cross bedding. See this? Smiley, happy face. Trough cross bedding. Trough cross bedding. Trough cross bedding. And this is the top surface of the top view of the trough cross bedding. When you see them from the top, they look like this. Okay? So the flow direction is this way, where these closes up. Okay? There's another trough cross bedding here. Okay? Flow direction this way. Another one here. Flow direction this way. Okay? Those trough cross bedding from the top, or top view, in the Cyrenaica Miocene Barqah state. Hammocky cross bedding, it has convex up hammock, okay, and concave up swale. So this is the hammock, and goes the degree, the angle or dip angle between 12 to 15 degrees. And this is very characteristic for the storm wave base. Okay, so this is hammock cross bedding, as you see here, and almost here flats. And then, yeah, you see there, on lap, okay. And this is HCS, hammocky cross bedding, forms at the storm wave base. Okay, here we're showing the flatbed parting lineation, which is ridge and grooves. If you look at this, you'll find groove and between them ridge. Groove, little groove, groove, groove. There's ridge, groove, ridge. The foam shows you the ridges and the grooves are white here. Okay, so this explains why the parting lineation is a combination of high flow regime and lower flow regime, which is the turbulent. When they have the high flow regime, the water current has linear. The high flow regime arranged in a linear method where it erodes these grooves, and the ridges in between is still under the laminar flow, so they're preserved. And this is in the photo from the Potlan's shoreline, Tolmetha area, shoreline in Barqah state by Hamad Bakar. And here the ridges and grooves, as you see here. This is the sense of current direction, either this way or that way. Same thing if you look here, grooves and ridges, grooves and ridges, okay? Grooves and ridges, but there's weathering here, so it's hard to find. And the sense of direction, current was moving this way or that way. And here, so see like grooves and ridges. This is a ridge here. I'm following this ridge. This is, and then groove, ridge, it's another ridge. Sorry. Okay. And another ridge, groove, and this is the sense of flow, direction of current, moving direction. By this, we can come to the like a real example from the Cyrenaica, the Cyrenaica Miocene and Barqah state, where we have composite sets. The lower composite set has larger scale planar cross bedding, topped by larger scale trough cross bedding, fiston, and it has like channels going across the larger scale planar cross bedding with soft sediment deformation. And then there's another composite set of planar cross bedding topped with trough cross bedding, but smaller scale, both of them, and then sharp surface, and then wave formed ripples, cross ripples, like the chevron one I showed you, and then above it, low angle planar cross bedding. So when the cross bedding have larger scale, we call them clinoforms. For example, this clinoform, and this is my student Ahmed Alwani, one of my best students and one of my best field assistants. So this is the clinoform, bottom set, fourth set, and then top set. Same thing, we can follow this, bottom set, fourth set, and top set. And here, this is the soft sediment deformation channel. Yeah, these channels, they show bottom. And this is a sigmoidal form, sigmoidal cross bedding formed during storms and from the spillover loops. This is just oolitic grainstone, made up of oolitic grainstone in the Cyrenaica and Miocene of Barqah state. And the clinoforms can be tabular. For example, this clinoform here shows tabular cross bedding. Another clinoform here. This is a zoom in, shows tabular cross bedding. Zoom in. Yes, this is the zoom in. It's like 2 meters, the tree. And this tabular clinoforms. Okay, planar cross bedding. They are tabular clinoforms in Cyrenaica state. Now the fossilized drain drops, drain drop impressions. This is in Fort Collins, Colorado, Horsetooth Reservoir. So the rain prints, the impression of rain prints is rain marks is preserved. This indication of surface exposure. Mud cracks or exposure surface, call them shrinkage cracks. And this is from the Miocene of the Cyrenaica Miocene. Exposure, surface exposure. And these the polygons of the mud cracks. So this is the Cyrenaica and Miocene of Barqah state. And here's mud crack in rippled white gypsum in the Miocene of Cyrenaica, Barqah state. Okay. And here's another example of mud cracked microbial white gypsum in the Miocene of Cyrenaica state or Barqah state. Another shrinkage cracks, we call them Sener's cracks. They form at the bottom or the interface of the water and the sediment surface. When the sediment has the higher salinity than the water inside the sediments will explode outside due to the osmotic pressure, and the sediment will fill these openings with same size or coarser size sediments. And then when they're compacted, they form these synersis cracks. And they're very, very dominant in the lacustrine or common under lacustrine sediments. And they can form, by the way, at the interface of the water sediments or within between beds too. Okay. This is a molar tooth structure, is exactly synersis cracks, but they are compacted. And these smaller tooths are very common in the Precambrian, especially in the argillaceous and calcareous sediments. Now we're done with the primary erosional sedimentary structures, secondary and depositional sedimentary structures, erosional and depositional sediments. Now we'll study the mechanics of particles movement in fluid. The fluids that we have, Yeah, which is, gas, the air, and liquid water. How sediments are transported. Transported as bed load, C, rolling, okay, or suspended, saltation, bouncing, or suspension, A, which is very fine, silt and clay. The saltation, sand size, medium to fine, and rolling, gravel size, coarser. So sediments that transported as bed load and saltation, we call them attraction deposits or channel carbet or bed load. Okay? Sediments that transported with B and A as the suspension and bouncing, we call them density currents. So it's combination of traction and suspension. And the mixture will give you sand, silt, clay. And suspension deposits, just suspension A, which is silt and clay, we call them low density current, okay, or low density deposits. Density current or density deposits, which is the sand and A and B, we call them this high density, and this suspension, low density. If you have sediment deposits, all of them, A, B, and C, we call them diamectite, which is all grain sizes, from clay silt to gravel size, which is ill-sorted, like in glacial. Okay? So, 3 types of sediment can result from the different source of fluid flow, liquid and gas. So traction deposits, which is bed load, transport, rolling, saltation. What that will give me? If you have traction deposits, that will give you cross-bedding generated by gravity, like rivers, wind, if the wind transported this traction. Deposits will give you sand dunes, and tidal force in the sea. Those will give you cross-bedding from traction deposits. Now, if sediments transported density current deposits, we call it high density, combination of traction and suspension, which is B and C. Mostly graded bedding, not cross-bedding, okay? Density currents, grade bedding, lack cross-bedding, generated by density differences, like thermal layering, turbidity, and salinity differences in liquids. Examples of density current deposits: subaqueous turbidity currents, aeolian turbid flow in the air, includes Neus ardens and certain types of high velocity avalanches and mud flow. So that will give me sand, silt, clay, and they are graded bedded more than cross bedded. Okay, then suspension deposits, low density, which is the finest, silt and clay, just silt and clay suspended. Examples: wind-blown loess, and loess, and pelagic detrital muds, nepheloids of ocean basins. So just silt and clay. Diamectite, complete range of grain size, poorly sorted from boulder to clay size, like in glacier deposits and mud flow deposits. Okay, so traction deposits, mostly cross-bedded, density currents, mostly graded, suspension, give me loesses and very fine sands, and diamectite give me all sorts like glacier and mud flows. Okay, let's go with aqueous process, water. Water transports sediments through traction, high density, and low density. Traction currents, unidirectional like fluvial channels, bidirectional like estuaries and marine currents, will give you cross-bedded sands and gravel size. In suspension, in density, high density, give you turbidized aqueous. Graded beds of sand, silt, and clay, so turbidized, graded bedding. Sediments from low density, like varve, nepheloid, and hypopycnal flow, hemipelgite, will give you massive and laminated beds of silt and clay size grains. Okay? Now, aqueous process, sedimentation from traction currents. We said bed load sediments, cross-bedded, sand and gravel grain size, unidirectional currents, said rivers and fluvial channels. That will give me all bedforms and their internal sedimentary structures. And the bidirectional traction currents, like in estuaries, open marines, for example, tidal, symmetrical tidal cycles will give me herringbone cross-bedding. Asymmetrical tidal cycle will give me cross-bedding and tidal mud bundles due to holostrom anomaly. B, waves. If I'm in the wave region and I'm having bid load, waves will give me wave ripples, chevron, cross-lamination, bifurcated top view, vortex ripples. Okay, so if you are having bid load in bidirectional currents, you'll have these types of sedimentary structures. Unidirectional current, you'll have this type of sedimentary structures. Now, if you had high density currents, what you will have? You'll have graded bedded in the aqueous process water, graded bedded sand, silt, and clay. So turbidity currents caused by differences in temperature, salinities, and suspended sediments. So the example, turbidity currents for these high density. Okay, internal structures of turbidity currents, Boma sequence and down current variations in the sedimentary structures of turbidites will give you TA, TB, TC, TD, and TE. That's Walker 1967. I'll show you here. So Boma sequence has TA, TB, TC, TD, TE. TA, coarse grained, massive, like this one here, erosional surface. Turbidite sequence, here TA. TB, laminated, so here TA. TB, laminated, is this one. TC, either convoluted or rippled, so here TC, deformance of sediment deformation, convoluted and rippled. TD, laminated, here we have TD, laminated. All these supposed to be sand size. And here grainy sediments in the limestone. And then you'll have TD, which is silt, and TE, the fine, the muds. We don't have these here in this sequence, but we have from TA to TD in the carbonate turbidites of Cyrenaica, Cretaceous. So here the turbidite sediments coming from the canyon and then spread out as loops at the basin and form these Boma sequences. Aqueous process water. So the third type, low density sediments, which is massive, that form massive laminated beds, silt, clay, grain size. The examples, var deposits. Var deposits forms in the coastal environments, give you light silt and dark clay couplets, like glacial and lakes. Those give you these couples of, light, dark, light one silty, dark is clay, rich in organic material. And you see here like dark, light, dark. So this is light and this is dark. Okay, so the light one, silty, the dark one is clay. Okay, now nepheloid deposits. And this is, by the way, let me go back. This is the var deposits in the lakes, var. Nepheloid deposits, suspended cohesive clay plus organic material, neither heavy to sink at the bottom nor light to float at the ocean water surface. So subtle density differences due to temperature and turbidity. And these nepheloids can be reworked by continuous geostrophic contour currents and could be mixed with some sand, mud and sand contourites. We call them contourites if we see that sense of transportation. We have hypopycnal flow. The hypopycnal flow, two bodies of no significant density difference. So nepheloid, there's a difference, but suspended, not floating at the surface, not sinking at the bottom. But hypopycnal, two bodies of no significant density difference. For example, Bilgite, no evidence of current action, graded laterally into bilgite, which is bilgites, red clays plus biogenic mud through ocean oses. So what features of all density currents give you clay stone, silt, massive, laminated? These features of the low density currents. Grain size. So lamination could happen due to grain size change due to chemical compositions. They have a lot of ripples, occasion traction currents. They have slump, slided deposits on slopes. Okay. They have cracked, syneresis cracks due to clay dewatering, spontaneously due to salinity differences. So these features in the aqueous suspension low density currents. Okay. Now aqueous processes. The difference between traction deposits and turbidity deposits. Traction, bed load, and turbidity. The traction cross-bedded deposit, which has sand, gravel, sediments, cross-bedded, clean, laterally restricted. This is the bed load. Turbidity, flat-bedded, graded, argillaceous, and then often laterally extensive, and made of sand, silt, and clay. Now the Aeolian, the second process, which is in the air. Aeolian and aqueous transportation and sedimentation show many points in common from traction carpets. Sedimentation from traction carpets, mainly sand, form sand dunes. Sedimentation from turbidity flow, newest ardents, volcanic ash and glass, forms ignimbrite deposits. And C, sedimentation from suspension, dust clouds, silt plus clay. That will form the lowest deposits. So this is this storm sand, sandstorm with clouds that form sand dunes, or deposit clay, silt and clay deposits we call lowest deposit. And the newest ardents is just volcanic ash blocks and glass, and deposit ignimbrite. This is ignimbrite, mixed blocks and ash and glasses, and very ill sorted, or you find it in this way. Both ignimbrite deposits. Now Aeolian process. Sedimentation from traction carbon. Sand dunes. Okay, give us sand dunes. We have lunate sand dunes, Barqah, and we have stellate or pyramid, and we have safe. Sometimes they call it star here. Safe and longitudinal, and we have transverse. Transverse is the only one that has net sedimentation. The other is sedimentation and transportation and reworking. Okay, areas of modern Aeolian sediment transport and sedimentation in the desert. Ice caps, around the ice caps, and barrier islands, okay? And along beaches, which is barrier islands here, in diverse climates, okay? So, do we have like sedimentary structures in the lunate transverse dunes? Yeah, we have cross lamination, cross bedding, and separated by erosional surfaces, flat bedded units, So phases of erosion and transportation. Safe dunes internally composed of mutual opposed forces. Okay. So dunes, bedding, any contemporaneous deformation. Do we have deformations? Yes. We have fracturing, we have slippage, and we have fold structures. So these are the types of dunes that we have: Barqah, transverse, Barqahnoid, longitudinal, parabolic, and star, which is the pyramid, this one. Note this along the beach, along the shoreline, those sand dunes here. Not all dunes in the deserts, by And this is the one that has net sedimentation. All the others, sedimentation and erosion, deposition and transportation. But this one has net sedimentation. Now, Aeolian processes, sedimentation from turbidity flow, which is news ardentist, volcanic ash, and glass shards. Resultant deposits, ignimbrite deposits. That's the turbidite flow in the Aeolian. Aeolian sedimentation from suspension, dust clouds, resulted in Lewis deposits. Tropical deserts and pre-glacial deserts. That's where we get the Lewis deposits from. Lewis of tropical deserts, laterally extensive layers. Description. Often of a great thickness, massive and slightly calcareous, and polygonal shrink cracks when weathered. Lewis of pre-glacial deserts. So they have two types of Lewises here. It has clay absent and medium silt size of silica particles. So no clay here, but here there's a clay. Okay? The ones coming from glacier, no clay, just medium silt size. Now glacier process, ice. Okay, type of sedimentary deposits associated with the glaciation. Traction, current deposits, aqueous, diffuse sand and gravel of fluvio-glacial outwash plains. Okay, that's fluvio-glacial outwash. B, suspension deposits, aqueous, varved glacial-like clays, so varves. And here outwashes. Suspension deposits, Aeolian, loose, medium silt size silica, no clay, just medium size. So let's look at them. This is the poorly sorted outwash plains, which is basically the tillite. And here laminated silt clay varve deposits. The light ones, silt, the dark ones, clays. Okay? So clay, salt, dark light. Okay, this is the outwash, poorly sorted sand and gravel. Here, laminated silt and clay varve. Here, another example, laminated silt and clay varve deposits. We see here we have light, dark, thick, light, thin, light, dark, thick, light, thin, dark. And within these thin lights, we have these clots. These clots, we call them drop stones. And if you notice, you'll find out here IRD deposit, which is the ice rafted debris, which is these. They form during melting season. The light one, the salty one come in during melting season, the same thing here. But the clays, the dark ones, just come in during the non-melting season. So if you look at the melting season MS, you find this. Okay? Silt and clay. But here, just clay, non-melting season. And you find the drops, these drop stones, during the melting season, the light ones. Okay? Now glacial processes, ice. Mechanism of a glacial transport, ice movement. One, in response of gravity in valley glaciers. Two, response to horizontal pressure in continental ice sheaths, slipping. These valley glaciers. Glacial process ice. Ice itself transports and deposits one rock type only. We call it diamectite or tellite. But diamectite, not all diamectites of a glacial origin. Could be mud flow. Tellite, genetic term of a glacial origin, we call tell, boulder clay, drift, and moraine. So when you say tellite, straight means glacial. But if you say diamectite, might mean glacial or mud flow. So what's the diamectite or tellite? Poorly sorted silica clays formed by pulverized striation grooves. Laterally extensive sheets more than a few meters thick. Diamectites also occur interbedded with the periglacial deposits, silt losses. Okay? Dropstone or diamectite or tellite. Okay, why you call dropstone? Because during melting, any sediments inside the ice, when it melts out, drops inside the sediment. So when you find dropstones, it means this is the melting season. And between, the non-melting. Okay? Dropstone, melting season. There's non-melting seasons. Okay? And here, dropstone again. That's glacial evidence. And this is tellite. This is tellite. Very L-sorted, different size mud to conglomerate size. And here, gravity processes. The gravity force is an integration or integral part of all sedimentary process, aqueous, aeolian, or glacial. We have gravity associated with them. Spectrum classification, dot 1963. Rockfall, avalanche, slide slump. Okay. So when the rockfall or avalanche is vertical, when you have slope and some water, you might go to slide and slump. So you need water, inclination, or semi-horizontal. And then if the water increases and the slope decreases, or have some slope, mass flow. You have more and more water and slope, which is debris flow, grain flow, fluidized flow. Debris flow, mud supported, when you increase water, it forms grain flow. When you increase water, it transforms it into fluidized flow. And then the last, when you add more and more water, you turn into turbidites. Okay? So rock flow form inland, heavy rain, freeze and thaw action, and in cold climates. In marine, when you have earthquakes, tides, and storm surges. Slide and slump, you need water, more water, inclined semi-horizontal. You have slide, undisturbed, sediment fabric, sediment laterally transported. Slump, disturbed sediment fabric, sediment sideway, downslope movement. Mass flow, you have debris flow, grain flow, fluidized flow. So mud flow, poorly sorted mixed grains, no constant viscosity. Add more water, it transforms to grain flow, which is grain supported and confined into channels, well sorted and clean sand. Fluidized flow, it's fluid supported. Channel confined, well sorted, clean sand. Dewatering dish pipe structure has dewatering. Turbidite is a different, shows you Bowman sequence, has sand, silt, and clay at the bottom of erosional surface, and might show graded bedding, massive, and deposit on the fan or basin floor with basal soil mark suites. So rock fall. This is rock fall, vertical. Rocks just drop vertically. And here avalanches, sand moved vertically. Yeah, here we have avalanche, or rock falls, and grain fall. Rock slides, you need the surface where the rocks just slide along. In this example rock slide. And slump, you need very defined surface. And sediments just ruptured and move along. And here another slump structure. And here heavy rain created mud flow or debris flow. And here debris flow. Now we're going back to the mass flow, which is debris flow, grain flow, and fluidized flow. As we said, debris flow is poorly sorted, has all grain sizes from mud to boulder, mud, sand, boulder. As we increase water, the debris flow will go to the stage of grain flow. But grain flows are grain supported, but always channel confined and well sorted. As we increase the water, the grain flow will change into fluidized flow, which is not grain supported, is fluid supported, channel confined, well sorted, and has dish or pipe structures. The grain flow here on the opposite always has, clasts scattered throughout the sediments. So let's see. If you have debris flow, this is debris flow, mud support, grain supported. It has a lot of sediments, matrix strength and buoyancy. So this is very L sorted. If we increase the water, that will become grain supported. And these two, by the way, confined to channels. The debris flow will become grain flow. It's confined to channels. Very clean sand with the clasts spread all throughout the layer of the grain with sharp bottom and top base and top. If we increase more water, the grain flow will becomes fluidized flow. And it's very clean sand, rarely no clasts. And this, when the sediments deposit in the channels, it shows dewatering structures, the dish structures, and the pipes in the fluidized flow. And if you increase the water in the fluidized flow, you go to the turbidite sequence, which is the BOMA sequence that we just explained. It says erosional surface with lithoclasts, lag deposits, massive at the bottom, and then rippled, and then has soft sedimentary formation, and then silt, and laminated sand, and then silt, and then clay. Okay, so let's show you the dewatering structure. This is the dish structure, and this is the pipes. This is another dish structure. Okay, that's dewatering in fluidized flow. That's fluidization station. Here's the debris flow. See all of these debris flows? Yeah, very L-sorted, deposited on turbidite sequences under it. Very well. And here turbidite sequence under the debris flow. And here turbidite sequence. And it shows these very erosive surfaces and repeated cycles of BOMA sequences. This is a massive TA. So here, let's go like sediment gravity flow process. 4 theoretical types of dispersive and supportive flow mechanisms that can achieve reduction in internal strength. So here we have mud flow. It's matrix supported. This is Bingham plastic. Okay, we increase the water, we go to the stage of grain flow. So the grains still can contact each other, and due to these contacts and hitting each other, they do the dispersive pressure, grains interaction, though still no Newtonian fluid. As we increase more water, the grains will never contact, and the grains will be dispersed upward under the influence of the buoyancy force due to the pressure of the water. And this is Newtonian fluid, high viscosity. And then as we increase the water, that will change into turbulent flow, which is turbulent fluid. So here mud flow or debris flow, and here the extreme, and the other extreme end is turbidite. So mud flow can be transferred to grain flow by increasing water, and then liquefied flow, and then turbulent flow. Turbulent flow will see BOMA sequences. Liquefied flow will see dish structures and pipe structures. And grain flow will see just very well sorted sand with scattered classes, and debris flow is very ill-sorted sediments. So with increasing water, this will change from debris flow into turbidity flow. And just to show that relationship here, high density turbidity currents. And now sedimentary process and their deposits. So we have three controls: gravity, fluidization, which is liquid, and traction. So if we start with the gravity, we have avalanche, vertical, and then slide, and then slump, and then debris flow. And here from debris flow, if we add more water, we go liquefaction, grain flow, and then fluidized flow. Okay, if the control is just liquids. If the control is liquids and gravity, we have bilguides, hemibilguides, nepheloids, those low density turbidity currents, and high density turbidity currents, we have turbidites, it's another type, and we have modified it by contour currents, contourites, and we have ripple and sand dunes, which is traction here in the air, in the ripples. Okay, so this is the full spectrum of the gravity processes, and they are deposits. I mean the sedimentary process and their deposits. Now, gravity processes. The gravity force is an integral part of all sedimentary processes, either aqueous, Aeolian, or glacial. So in conclusion, the gravity-related sedimentary processes range from avalanches via debris flow, grain flows, and or fluidized flow to turbidites. This is the extreme end. Okay. This spectrum is marked by decreasing gradient slope and sand concentration and increasing velocity and water content. The slope failure may have been triggered by one or more, of several processes, including earthquakes, loading, oversteepening, and consolidation or under consolidation, rapid sedimentation, gas hydrate decomposition. Debris flow, this is a note just here. Debris flow grades with increasing water content into sheet flow, which is the midway between grain flow and traction currents. Now, some information about the beddings, bedding thickness, type, and contact. And we talked about this: less than 3 millimeters thin laminae, less than 10 millimeters thick laminae, more than between 10 and 30 millimeters thin, very thinly bedded, between 30 millimeters and 0.1 meter thinly bedded, between 0.1 and 0.3 millimeters medium bedded, between 0.3 and 1 meter thickly bedded, and then very thick bedded. So here beds, either, if they're planar, wavy, or curved. If it's a planar, is it parallel, or they're non-parallel, or they're discontinuous? The same thing, wavy. Is it parallel, non-parallel, or parallel, non-parallel, and discontinuous? Curved. Is it they are parallel to each other, non-parallel, or wavy? And here the base is that sharp base of contact between two beds, sharp and erosional. You have clastic lags, or gradual, coarsening upward, or gradual, fining upward, or transitional. So here you have mud and sand, but here you have alternation of mud, sand, mud, sand. This is transitional, okay? Not this. This is gradual. Or the boundary is mud rock parting, or the boundary is mud crack exposure, or roots or burrowed surface, which is mainly firm ground, or loaded structure, loaded contacts, like with loads. Or sometimes the exposure, paleokarst exposure, or encrusted bored surface or the ground, or phosphate contact between two iron manganese crust hiatus, or pressure dissolution seams, or stylolites. So these showing the possible range of contacts between beds. Now, post-depositional sedimentary structures, which is deformational sedimentary structures. Okay, so these post-depositional sedimentary structures, the ones has horizontal, dominantly horizontal slump and slides that happen in brittle sediment. Sediments possess shear strength, and the other ones dominantly vertical load cast, pseudo nodules, convolute or convolute bedding, recumbent facets, convolute lamination. Those have plastic sediments, lack shear strength. Okay, so let's look at this. This is a slump here. Shows slumping, so that has like horizontal movement, and this is, by the way, this is the shear surface or the sliding surface. And this is the slump of the Cretaceous outcrop, turbidite outcrops in Cyrenaica state. The slump again in the Eocene of Cyrenaica state. Old beds here. And this is soft sedimentary formation in the United States. And here plastic deformation in the Cretaceous of the Cyrenaica state, which is almost plastic debris flow. And here, convoluted shale beds. Lamini is convoluted due to soft sedimentary formation in the Cretaceous of Cyrenaica. And here the overturned facets in the cross bedding. And here the load structure, this is a flame loading structure, so sand loading down into this shale bed. Okay, sand, shale. Okay, those flame load structure. And you might have balls and pillows. Your balls and pillows, sand inside the mud, balls and pillows, okay? This is in Fort Collins in Denver in the United States. Loading structure. Or you might have deformational dish structures like these here, those dish structures, and these the pipes, the fluidized flow. Or you might have liquefied sand dikes due to liquefaction and fluidization. So the sand goes up and it's always connected to the original sand layer. Sand dikes are introduced as liquefied quicksand into water saturated mudstone. And here we have another particular variety of sand dikes. We call it sedimentary bodinage, which is shale layer forming nicks and disconnected, and the sand injected inside from top and bottom. Okay, and this and the shale shows like clear floating blocks floating in the sand. And this is this is sedimentary. It's the opposite of the tectonic bodinage or structural bodinage. The structural bodinage is the sand or limestone, the hard layers having nicks and the shale flowing inside. But the sedimentary is the opposite. The shale fragmented and forming nicks and the sand flowing inside it. The sand volcanoes, liquefaction and fluidization, and these mud volcanoes, liquefaction and fluidization. Here there's a contrast between mud cracks that tapering down and the sand dikes that coming from the source sand and going up through the rocks, and always connected to the mother sand feeder. And here there's another deformational structure, TP, formed due to crystal expansion. So this is the TP structure here. So, this is the United States, and this is tidal. And here another TP structure. See this, and this is the expansion of the salt. This is evaporite, and this is mud cracked TP structure. And there's another TP structure. This is my nephew Salah. He's helping me. He's a geologist. So do you see this? He's just standing on the evaporite bed, and these just TP structures. He's enjoying hammering that. So to the evaporite crystal expansion, and we have, this is evaporite layer, and if you look at the top of this evaporite, you see TP structures all the way. Okay, so it's crystal expansion again, and here we have cone in cone structure, diagenetic, due to displacive crystal mechanism. So these cone in cone structures, you see them. Same here, you see the cone and cone structure. The top side, this is the bottom side of cone and cone structure. And here we have the salt halite cast hopper, and that means the hypersaline depositional environment. So this is the salt halite cast hoppers. You know, usually the cast hoppers, they're cubic shape, you know, and why they called hopper, because at the center the growth is lower than the edges. It's like a depression inside. That's what they call it, hopper shape. Okay. Cubic, like, has empty center. And now stylolites. Stylolites, we'll talk about here stylolites and the solution seams. Those diagenetic too. So stylolites, as you see here, limestone. And here we have dissolution seams where the residual undissolved sediments form these dark boundaries. And now again, here we have stylolites, and see the black dark residuals in these, you know, solution going even through the grains. And here we have the solution seams here, stylolites going across oolitic grains. So now biogenic sedimentary structures, or ichnofacies, we can group them to two major groups, traces and burrows. Traces is just on the surface of the sediments due to resting, crawling, or grazing, all of these traces. Burrows within the sediments due to dwelling, feeding, and escape burrows. And there's a good so as we said here, grazing, resting, crawling, these just traces on the surface. Trace, trace, trace. The rest, here's those burrows, those inside the sediments. Okay? Due to dwelling, feeding, and escape. So feeding structures, chondroids, zoophycos. Here, dwelling, Scolithus, Ophiomorpha, Thalassonid, Diplocriterion. Those common in shallow marine environments. So let's go back to and grazing here, nerites and helminthoids. They're common in deep environments. So let's go to here. This from Selley 2000, Selley 2001, terrestrial, intertidal, subtidal, marine. So here all traces, terrestrial, common. Scolithus, vertical burrows, and the other one, the Diplocriterion. The Diplocriterion, they are common in intertidal. And here, Zoophycus, Cruziana, and all these inclined burrows, they're common in subtidal. And the Neritis ignofacius, which is a trace, is common in the very deep marine. So vertical burrows, intertidal, inclined burrows, subtidal. Here traces. This is crawling, dinosaur. It's real, dinosaur traces. Cruziana, traces. Crawling, trilobite tracks on the surface. Starfish, traces, resting. Helminthops, traces. This is grazing. Nerites, grazing, which is traces. Okay, and here we have burrows. This is dwelling burrow, thylacinids, thylacinoids, which is a crustacean burrow of intertidal, shallow subtidal environment. And here we have the Diplocriterion, which is the U shape, and it has sprites here. Curved shapes, we call them sprites, concave up. U-shaped vertical burrow, dwelling, same thing here, sprites. And we have another burrow, we call it dwelling burrow, which is ophiomorpha. It's vertical burrow lined with pellets and muds. So it has pellets and muds here lined on. This is a crustacean burrow of intertidal, shallow subtidal. No. This is not crustaceans. And this is vertical burrow lined by pellets or muds. And here we have a dwelling burrow, which is Scolithus. Let's repeat it over and over and over. Simple vertical burrow of intertidal environment. In feeding burrows, Zoophycus. This is the ficus. It's a feeding burrow. And we have feeding burrow crinoids. This is how it looks from the surface. And here cross section, how it looks, the crinoids. And then bioturbation, you might see it mottled surface. Enhance it by diagenesis, give it different color. Here, thylacinoids from limestone, bioturbate limestone in Barqah state. Cyrenaica, Miocene of Cyrenaica state. And here we have bioturbation, which is again thylacinoids, tertiary, Cyrenaica, Barqah state. And here we have, this is a burrow. You follow this burrow. And there's another one here. Tertiary of Cyrenaica state, Barqah state, and there are more other information about the bioturbation if you're interested. And now I'm going to go to the important stratigraphic surfaces. And here, note shrinkage, cracks, and raindrops impressions are primary depositional sedimentary structures. So this surface, we call it hard ground. If you look at this surface, if you follow it, okay, you'll notice here, this one cut through, so the fossil is cut. And this surface is very hard, very cemented. We call it hard ground. This is from Permian Basin, West Texas. And you might find the green, green glauconite with a black sand size grains, maybe phosphate. This is from tertiary of Barqah state, tertiary of Cyrenaica, Barqah state. And here the same exposure. So this is low rate of sedimentation. It's very important surface. And this is another one, phosphate. And here fossilized raindrop marks. And this is another surface of exposure, which is very important stratigraphic surface. And here shrinkage cracks, which is the muddy cracks, another surface of exposure in the Miocene of Cyrenaica state or Barqah state. And these very important surface, important when you notice them, tell you about the surface exposure. Now, paleocurrent analysis. Cross-bedding and the inferred paleocurrent data. We can use more than any feature that indicates direction of transport is a paleocurrent indicator, e.g. cross-bedding, channels, bottom marks, anything. So what's the variation? The scale, mean direction, and variability. This is about cross-bedding. What the scale? Scale of cross-bedding is a function of current velocity. Orientation of cross-bedding is a function of the direction of the current flow. Variability, function of stability of the current system over the geological short time interval. And the variability could be related to tectonic stability, could be related to sinuosity of the river, or reflect environmental differences. Okay. Here, Allen's, he said the larger scale cross-bedding, the more deeper water. And here we have angle of repose. The maximum angle of inclination observed is 34 degrees for the cross-bedding. Degrees, the angle commonly cited as the angle of repose of sand. So angles of inclination, therefore, in excess of 36 degrees indicate post-depositional deformation. Now, paleocurrents, they have these patterns: unimodal, one direction; bimodal, and bimodal bipolar, have two directions; or oblique, bipolar, two directions. Or poly is more than one direction, polymodal. Those are the patterns. When you finish your work, you find the azimuth of these patterns. So paleocurrents analysis, the bed form hierarchy. There is a hierarchy. We have mesoforms, and we have microforms, mesoforms, and macroforms. The microforms, we call them sixth of the grade, like ripples, less reliable. The mesoforms, like cross-bedding and spillover loops, they are reliable, but they are less reliable than the macroforms, like channels, which is first and second, rank. And for here, the inferred channel's vectorial data or direction is more reliable than the cross-bedding vectorial direction, and the cross-bedding vectorial data are more reliable than that of ripple wave cross-lamination. So channels more reliable than cross-bedding, cross-bedding more reliable than ripples. So what's the possible paleocurrent data presentation? You can present it as histogram or as Rose diagram. Okay, those are the two ways of presentation. In data interpretation, must be associated with sedimentological study. For example, alluvial environment, you have braided and meandering. Braided give you unimodal, low variability. Meandering will give you unimodal and bimodal or poly. Unimodal, high variability. Aeolian will give you unimodal and bimodal or polymodal mode for the paleocurrent. Deltic environment, unimodal. Shoreline, each environment like marine turbidites, unimodal. This is for local currents. Regional, for example, alluvial system, often fan-shaped, slope-controlled. Fan-shaped or meandering, slope-controlled, often centripetal basin fill, and for meandering, fan-shaped, for deltaic, regional, radiating, shorelines, generally consistently oriented onshore, offshore, or alongshore. So these are the interpretations. And here are the ranks, like 1, 2, 3, 4, which is microform, mesoform, and macroforms. Macro, these four, which is basically ripples, larger scale cross-pitting, and spillover loops, and the rest is just channels and systems. Okay. And here, paleocurrent data collection. So as we said, you have to associate your paleocurrent data with sedimentological study. So when you find the cross-pitting data, for example, you have two things. This is the direction of the, so you see the dip is going this direction, so this direction of flow. So you need the direction of the flow or dip direction, which is 70 degrees northeast, and the inclination, angle of inclination, we find at 25 degrees, okay? We need to measure this. We're not using it, but we need to measure it because we want to make sure that our cross-pitting not tectonically deformed, not more than 36 degrees. But what we use, just this number here and type of the cross-pitting, small scale or larger scale. Okay, so what do I do with my data? Group it like larger scale, okay, and small scale. Okay, this scale, small scale, and larger scale. For example, this is M, has 5 reading, bit number 5, and then I measured planar, larger scale cross-pitting, okay, and the direction was 70 northeast, and inclination degree was 25, and how many readings I did take from that? I did take 2 readings. I do the same thing for another section, for example, Z, trough cross-pitting, and the dip direction 85, and the inclination 20, and I got 4 readings. This is larger scale. Now small scale bits. Small scale, I do the same thing. Name, section name, bit number, and then take the information. Okay, so this way I have sediment stratigraphic section, and this is my section, this is bit 5, this is real data. I divide the intervals 1 to 30, 31 to 60 on. So from 0 to 36, I divided them to 30 degrees each, 12. And then take the midpoint for each class, 15, 45, 45. And then, so between 1 and 30, how many readings did I make? 11. Between 31 to 60, how many cross-pitting readings? 3. I put how many readings? If I did no readings around that range, just omit it, 0. And then I find the frequency, so the total here of my readings, the N total, which is Fi, I divide each one on the total and get percentage frequency. This frequency should be total 100%. And then what you do, F sine theta, this is Fi multiplied sine of this, and then Fi multiplied cosine of this. So you find sine, cosine for each reading. And then sum all of these sines, and then sum of all these cosines. That's what you need. And then what you do, find the arctan of the sum of all sines, arctan of sum all cosines. This is the azimuth. And if you want the magnitude, apply this equation, R. Okay? And then if you want dispersion and strength, put R over Fi or N, number of the data, times 100. But this is the azimuth. This is the equation for the azimuth. The rest is extra. And all what you need, these two. Paleocurrent data manipulation and calculations. So you have the vertical component, W summation of I sine theta, and then the horizontal component, V summation of I cosine theta, and then the vector mean or azimuth, the vector mean theta equal 10 arc W over V. This is the equation from Harpoff and Miriam, 1968, page 42. And then the vector magnitude R equal W squared plus V squared, square root of both the terms. And then the data number, N, is exactly Fi, so number of reading. The vector dispersion or strength, L equal R over N times 100. And by this, we reach at the end of this long lecture, but very important, combines sedimentary structures and transportation together on laws of physics. And this is the take-home message, which is basically the outlines. And now we'll take 3 minutes with the national anthem of Cyrenaica state. رحم الله الأمير ومن معه من البركة.